For those of you who are just joining us, welcome and thanks everybody for being here today. Before we dive in, I have just a quick couple of housekeeping items for everybody. Today's session is being recorded and we'll be sharing the recording on our YouTube channel later this week for anybody who wants to revisit the material or share it with teammates who couldn't attend live. To help keep audio clear during the presentation, attendees will remain muted throughout the webinar, but we absolutely encourage questions, so feel free to drop them in the chat at any point during the session, and then we'll have some time for questions at the end. With that, I will pass it over to Inder.
Alrighty. Hey everyone, my name is Inder Dylan and I'm a meter engineer at GridU. I've been working in the metering space for about 3 years now, mainly focused on system configuration, troubleshooting, and working through different setups across projects. Today, I'm going to walk through how we approach metering method selection, looking at standalone systems, peer-to-peer, and dynamic loss compensators, which I'll be referring to as DLC further in this presentation, and how those decisions, the info systems, are designed, communication, and overall performance. I'll also spend some time on SCME and ISOME, since that tends to be a big part of how systems are structured, especially when it comes to data flow and compliance. One thing worth flagging upfront is everything in this presentation is specific to CalISO. All the requirements, classification, and processes we're walking through today are based on CalISO Business Practice Manual. If you're working in other ISO markets, the principles are similar, but the specific rules might differ. And I'll try to keep things pretty practical and focus on how these decisions are made in real projects, and we could save questions for the end. So here's a quick roadmap. So first, I'll frame why meter placement matters and what changes when losses are either inherently measured or have to be modeled. Then I'll go through three main metering methods we've been using in projects, so standalone, peer-to-peer, and DLC. And after that, I'll show how data moves because the communication design is what connects the site to CalISO. And then I'll shift into ISO settlement classification, including what people often call ISOME versus SCME. And I'll finish with conversion logic when each model makes sense and the main design takeaways. So just to kind of level set on what we're trying to do here. So the main goal is to understand the different metering communication methods and, more importantly, how to actually choose between them depending on the system. I'll be comparing approaches like standalone, peer-to-peer, and DLC and walk through where each one makes the most sense. And from there, I'll focus on how selection is really driven by things like system requirements, communication needs, and overall constraints. And then I'll tie that into SCME and ISOME, looking at how those configurations impact systems and when conversion between the two becomes relevant. So just before we get into the technical details, I want to spend a minute on timing because this is one of the most common ways projects get into trouble. Metering strategy isn't something you figure out at the end of a project. By the time you're close to commissioning, your transformers in the ground, your communication infrastructure is designed, and your PPA terms are locked. So if any of those conflicts with your metering requirements, you're dealing with expensive late stage changes. And the guidance we work from, which are start your metering method evaluation at least 24 months before COD. That gives you time to assess the physical site constraints, understand your regulatory obligation under the CAISO BPM, and evaluate your market or PPA requires. Excuse me. So, and 18 months before your target sync date with CAISO, your metering method needs to be finalized. Not in draft, but finalized. And from that point, equipment lead times, CAISO certification, and SQMD plans development all needs that decision locked. The Venn diagram here on the right shows three areas that have to align: regulatory requirements, primarily the CAISO BPM, physical requirements, meaning what the site can actually support, and market requirements, which includes your PPA terms and settlement structure. The optimal metering method sits at the intersection of all three. If any one is misaligned, something has to change, either the metering approach, the design, or the contract. And with that, we'll get started. We'll start with the simplest method, standalone metering. The concept here is exactly what it sounds like. You have one revenue meter. At the single meter represents the entire site's output. It measures net power, kilowatts, and reactive power, kVAR, at the point of interconnect. The typical placement is on the high side of the step-up transformer. We'll look at what that means here in a moment, but short version is high side placement is preferred because it automatically captures transformer losses in the meter. Standalone is the right choice when your site is simple. One resource, one transformer, one interconnect point, no intermeter communication needed, no RTAC, no calculating meter, just one meter doing one job. So standalone works well within its scope, but the scope is pretty limited. And let's talk about why meter placement matters here, because this is one of those things that seems like a detail, but has real implication. When we say high side placement, we mean the meter is installed upstream of the step-up transformer, between the transformer and the grid, at the higher voltage level. The key advantage here is that transformer losses are automatically captured. Think about it this way. The transformer itself consumes a small amount of power, typically somewhere between 0.3% and 1% of the throughput, as heat and magnetic flux. When the meter sits above the transformer, it reads what's actually being delivered to the grid. Losses are already baked in. So this means no correction factor is needed. There's no RNX compensation formula to configure. What the meter reads is what KISO settles on. Pretty clean and direct. High side placement is the preferred configuration for this reason. It simplifies commissioning, reduces the chances of configuration error, and produces a reading that directly reflects POI delivery. So now, if we expand the system into multiple resources, for example, both PV and BESS connected behind the same transformer, the metering configuration itself doesn't change. The same high side meter continues to measure total real and reactive power leaving the site. However, the measurement now represents the aggregated contribution of all resources. There is no way to distinguish how much power is coming from each individual resource, and no way to associate losses with specific unit. And from an operational standpoint, this becomes a limitation when resource level visibility is required, whether for performance tracking, dispatch verification, or more detailed settlement. So at that point, the single aggregated measurement is no longer sufficient. Okay. Excuse me. Now, if we flip the scenario here, what if the meter is on the low side of the transformer? So low side mean the meter is installed downstream of the transformer, closer to the generation equipment, typically 34.5 kV or smaller. A low side meter reads gross output from the resource. It measures power before it passes through the transformer. Since the transformer consumes some of the power as loss, the meter is reading more than what the actual gets to the point of interconnect. And to fix that, excuse me. Okay, where were we? So in order to fix that, you have to apply loss compensation correction, a formula derived from the transformer's R and X parameters that adjust the metering reading down to what was actually delivered at the POI. This correction is mandatory. It must be configured and validated before the site goes live. So the structure of the system may look similar, but the reference point of the measurement has shifted to low side. and that has direct implication on how losses are handled and how values are interpreted. So, how does losses actually work? And this is where transformer test reports become a metering document. Each transformer has a factory test report, also called a certified test report or CTR, or manufacturer test report. The report contains the data you need to calculate losses. So things like impedance, excitation current, load losses, and no load losses. From those values, you derive two parameters, R and X, where R represents the resistive losses, the real power consumed by the transformer. Excuse me, quick second. Okay. So X represents the reactive component. So together, they define how transformer losses scale with the current flow. These R and X values get programmed directly into the revenue meter as part of its configuration. The meter has continuously applied the correction formula to its readings, adjusting its kW and kVAR output to reflect the PUI equivalent value. Quick, one thing to flag, the accuracy of the correction is only as good as the transformer test data. So if the test report is either old, uses the estimated values, or was done under different excuse me, or was done under different loading conditions, the correction may be inaccurate. So that's worth verifying before commissioning, during our meter testing, or before that. So now moving into peer-to-peer. Peer-to-peer metering is the step up from the standalone, designed specifically for sites with multiple resources, that each individual feeder has a meter. This diagram shows, excuse me. So the diagram on the right shows a simple method of peer-to-peer. Each resource is in this case, BESS and PV has its own revenue meter installed on their respective feeder. In addition to that, we still have a meter on the high side of the transformer, and this is what we refer to as calculating meter. Instead of one meter doing everything, the system now relies on all these meters working together to represent the site. This allows us to monitor power flow for each resource. So now that we see the layout, the next step is to understand how each meter is actually being used. Quick second, I will look at this. So let's look at the physical configuration and what each meter actually does. The resource meter down here at the bus are measuring the real and reactive power coming directly from each resource. These are your local measurements, capturing what each unit is producing individually. The high side meter, on the other hand, acts as the calculating meter. This is the brains of the peer-to-peer method. The calculating meter has two jobs. First, it measures the transformer's high side conditions, voltage, current, power factor. Second, and this is the critical part of it, it uses that data along with the readings it receives from the resource meter to calculate how transformer losses should be allocated across resources. And the allocation isn't equal, it's proportional to each resource's contribution to the total site output at any given moment. A resource generating more power bears a large share of losses, and that loss allocation is then sent back to each resource meter, which applies it to produce a corrected POI equivalent reading. And for that to work, all of these meters needs to stay connected. So for peer-to-peer meters to work, all of these meters need to communicate continuously. Excuse me. This is typically done over Ethernet using Modbus TCP. The meters are connected on dedicated isolated LAN, typically via managed Ethernet switch. And static IP addresses are assigned to each device. The calculating meter pulls resource meters continuously, typically few seconds to maintain a real-time loss calculation. Excuse me. Each resource meter is sending its real-time electrical measurements like real power, reactive power, and current to the calculating meter. And now we might think, what happens if the link goes down? And this is actually pretty important. The meter has a failover mode that gets programmed into the meters. So when the communication link drops, the dynamic loss calculation stops. The resource meters can no longer receive live corrections from the calculating meter. And at that point, they fall back to a set of pre-configured static RNX values. And yes, that is the same kind of excuse me. And like I was saying, that is the same kind of transformer-based loss method we discussed for standalone metering. And those static values are still valid. They're just not real-time values. The reading remains compliant and usable for settlement. They just won't reflect dynamic changes in load distribution until the link is restored. So the loss calculation process in peer-to-peer system is continuous. The calculating meter pulls each resource meter to obtain their current, real, and reactive power along with currents. It will then determine how power is flowing through the transformer and the line to the point of interconnect. From there, it determines the losses associated with that operating condition. It also identifies which resources are actively contributing to that flow. Since loss allocation depends on which units are actually producing or charging at that time. So for example, if the PV contribution is 60% of the total output and the BESS is contributing 40%, then PV is allocated to 60% of the loss and BESS gets 40. So the allocation is proportional. Once those losses are determined, the next step is how they get applied. So after the calculating meter determines the losses, those values are then sent back to each resource meter. Each resource meter then applies its portion of the losses to its own measurement. This adjusts both real and reactive power values at each resource. And because of that adjustment, each meter now reflects what its contributing would look like at the point of interconnect, rather than just at the bus level. So instead of relying on a single point at the top, each resource is now effectively representing its own POI equivalent output. And that's what allows this setup to maintain both accuracy and visibility at the same time. And that's where the peer-to-peer really solves the limitations we saw earlier in standalone. So we talked earlier about where standalone falls short. With standalone, you get aggregated output only, no visibility into what any individual resource contributes. Excuse me. And that loss handling is static. So you configure the RNX once it doesn't update based on how conditions are at the site. And peer-to-peer solves both of those things directly. Per resource visibility is maintained continuously. KAISO can see individual readings for each resource throughout every settlement interval. And the loss allocation is dynamic. So as the condition changes, as the battery charges and discharges, as the clouds cover various PVs output, as loading shifts, the loss calculation updates. The corrections are always based on what's actually happening at the site, not fixed parameters set at commissioning. And the result is accurate, POI equivalent output per resource all the time. And this is why for hybrid and multiple resources, we would typically do peer-to-peer, not because standalone is technically wrong, but because it simplifies, excuse me, because it simply doesn't provide the data needed that multi-restores requires for settlement. Excuse me. So peer-to-peer is more capable than standalone, but it's not without constraints. So peer-to-peer relies on meter-to-meter communication, and there are practical limits to how many meters can participate. Excuse me. How many meters can participate in the direct communication arrangement before it becomes hard. So as the site grows, more inverters, more batteries, more meters. Peer-to-peer hits its ceiling. So on failover, once the link is dropped, the sequence is pretty straightforward. The communication link drops, the dynamic updates stop, the meters fall back to pre-configured static RNX values. Settlement data remains valid, but it's no longer dynamically corrected. When the link is restored, the dynamic mode resumes automatically. The third is more about meter capabilities, or excuse me, compatibilities. Peer-to-peer requires that all meters in the system can communicate using the same protocol, typically Modbus TCP. So if you're adding a new resource with meters from different vendors, say mixing ions with SELs, the direct peer-to-peer communication may not possibly do the protocol. And these limitations lead directly into our third metering method, which is DLC. Excuse me. So dynamic loss compensation, also known as DLC, is the third and most sophisticated metering method. It's designed exactly the scenarios where peer-to-peer runs out of the road. The fundamental difference between peer-to-peer and DLC is the method. In peer-to-peer, the meter communication directly with each other. In DLC, there's no meter-to-meter communication at all. Instead, an external controller, in our case called an RTAC, a real-time automation controller, sits in the middle and manages everything. Excuse me. The RTAC is a single source of truth for loss calculations. Excuse me. It pulls all resource meter, collects their data, performs the loss math centrally, and then pushes corrected values back to each meter. The meter themselves are an essential passive data source and are correction recipients. And this method solves the scaling and compatibility problems that peer-to-peer had, because all coordination flows through the RTAC. You can have many meters as the RTAC can support, and that's much higher ceiling than meter-to-meter communication or peer-to-peer. Because the RTAC communications with the meter using common protocol, either DMP or Modbus, you can mix meter types from different vendors without compatibility issues. So in DLC configuration, each resource still has its own revenue meter, measuring local output. That part doesn't change from peer-to-peer. What changes is how the data moves. Instead of Modbus TCP communication between meters, each resource reports its data to the RTAC using DMP3 or Modbus. The RTAC acts as the hub. It collects data from all meters, runs the loss calculation, and then writes the loss values back to each meter. This centralized design simplifies troubleshooting and scales more effectively than distributed peer-to-peer model. So before the RTAC can calculate losses, it needs a model of how system behaves electronically. The model is built using transformer test data, which provides impedance characteristic of transformer. From that, we derive equivalent resistance and reactance value, which represents how the transformer contributes to both real and reactant loss. In addition to that, line impedance is also included to account for losses between transformer and POI. So what we end up with is a set of R and X values that represents the overall system. And these values aren't changing in real time. They're based on physical characteristics of the equipment, but they define how losses will behave under different operating conditions. So at this point, we've initially built the foundation of loss calculation. Excuse me. Once the RTAC has both system model and real-time data, it combines the two to calculate losses. So it takes in real and reactive power data values from each meter along with current measurements and uses that to determine how power is flowing through the system. Using the R and the X value from the model, it applies power equations to calculate both real and reactive loss across the transformer and the line. So that combines is what allows the RTAC to calculate losses dynamically. Even though the model itself is fixed, the output changes continuously as the system loading changes, which gives you more accurate representation than purely static approach. Once those losses are calculated, they need to be pushed back to the revenue meters. So after the RTAC completes its loss calculation, it writes the corrected values to each resource meter. Excuse me. The meter uses this information to adjust its reported kW and kVAR readings so that the value ultimately submits for settlement reflects the resource proportional share of delivered energy at the POI. And this is the final step in DLC cycle and produces the same end result as peer-to-peer metering, accurate per resource POI equivalent data, but through a centralized rather than peer-to-peer. So the reason we go through all that is because peer-to-peer isn't always feasible. So there are four primary drivers for transitioning from peer-to-peer to DLC. First has a practical communication limits. Beyond a certain number of meters, the peer-to-peer model becomes unreliable. Second, the site with high resource count requires centralized coordination that only RTAC or any other controller can provide. Third, sites with mixed meter manufacturer faces compatibility challenges. A SCL meter and an ion meter typically cannot exchange data directly over Modbus TCP, but both can communicate with an RTAC via DMP. And last, when system level reliability and auditability are prioritized, centralized DLC method provides a single point of control and cleaner data path. Excuse me. So now, looking at how communication works in the field, this table shows the full data path from the meters all the way to CAISO. So starting at the site, the revenue meters are measuring real and reactive power along with voltage current. The data is sent to CAISO rig, which acts as a central point for collecting and consolidating meter data. The rig collects data from all meters, validates it, and prepares it for transmission. And from there, the data moves through ECN network, passing through the site's communication infrastructure before being sent to CAISO. Once it reaches CAISO, the data is used in two main ways, the real-time operations and settlement. The real-time values like kW, kVAR are used differently in EMS for monitoring system conditions. And on the settlement side, those values are recorded in metering load profiles collected through MV90, typically in 5-minute intervals. Now, while that's overall path, what actually changes is how the data is handled within the site before it gets there. And this slide summarizes the communication differences between the three metering methods we discussed. In a standalone configuration, a single meter reports directly to the rig. No internal meter communication is required. And in peer-to-peer system, the resource meter and calculating meter exchanges data over Modbus TCP. Each resource meter submits its own corrected value to the rig. And in DLC method, all meters report to the RTAC using DMP, or if they're ions, Modbus TCP. The RTAC performs all calculation centrally, and then the compensated values are then forwarded to the rig in all three cases. The data path from the rig to CalISO remains the same. Excuse me. So we will now shift from metering configuration to entity classification. ISOME and SCME defines who is responsible for meter data quality and how the data gets submitted to CalISO for settlement. These are not hardware categories. They're how operational and designations that carry different responsibilities for resource owners and scheduling coordinators. So ISOME stands for ISO meter entity. In this classification, CAISO takes direct responsibility for meter data by pulling the site's revenue meter itself. CalISO is also responsible for validating and processing that data for settlement purposes. SCME stands for Scheduling Coordination Metered Entity. And in this classification, the scheduling coordinator submits the settlement meter data to CAISO on behalf of the resource. The SC and the owner jointly takes responsibility for data quality, and that responsibility is formalized in an approved settlement quality meter data plan, or SQMD plan. So both ISOME and SCME can support standalone and peer-to-peer meter configuration. The key difference is that DLC, dynamic loss compensation, is the only available under SCME. This is because DLC involves an RTAC performing complex, which means that CAISO won't have any visibility to the meters, so it's external signal to the meter, and that falls under SCME. SCME also generally offers more flexibility in how peer-to-peer is configured. Under ISOME, CAISO needs to be able to pull the meters directly and interpret the data without additional processing from the SC. And in this table, pretty much summarizes the core operational differences between ISOME and SCME. The most important point to highlight is the final row. That actually settlement values that CAISO receives are comparable regardless of which classification is in use. Both ISOME and SCME produces loss compensation, meter data that is used for energy settlement. This distinguishes in entirely how that data is produced, who is responsible for its accuracy, and the documentation required to support it. So now I want to spend a moment on something that trips up a lot of projects: the relationship between your market obligation, your PPE, and your meter classifications. So some PPAs or off-taker agreements, specifically whether the resource must be CAISOME or SCME, that might look like a commercial decision, but it has direct technical implications. So if your PPA says CAISOME, but your site physically requires a DLC, maybe because you have too many meters for peer-to-peer, or you're mixing up meter types, you have a conflict. And here's the key principle: the BPM trumps the PPA. CAISO's business practice manual defines the metering requirements that governs your site. If the physical configuration requires SCME to support DLC, that requirement stands regardless of what PPA says. What that means, practically, the PPA needs to be revised and not the metering, or the metering can be revised, but the conversation is a lot easier to have 24 months before COD than 6 months before commissioning. And this is exactly why the three-way alignment, regulatory, physical, and market needs to happen early. Catching a PPA conflict at design stage is a contract revision. Catching it at the commissioning is a project delay. So the process of converting from ISOME to SCME involves 4 key steps. First, the site's metering configuration must be assessed to confirm it can support SCME, including verifying the communication path and the data submission capabilities. Second, the scheduling coordinator develops the SQMD plans, which is formal document that describes how the settlement quality data will be produced, validated, and submitted. Third, KISO reviews that plan and formally approves the conversion. Fourth, once the plan is approved and the effective date is reached, the SE takes over the data submissions and KISO stops pulling the site meters directly. And now if we were going the other direction, SCME to ISOME, means the site is moving back towards more standard KISO pulled metering setup. This is usually metering reduced or removing custom settlement logic, aggregation, or external calculation method, making sure the site can meet CalISO certified metering requirements. The benefit is that the settlement process becomes more standardized and KISO takes on more of the direct data processing role, but the trade-off is less flexibility. If the site changes later, those changes may need KISO approval and could trigger additional validations or recertifications. So when deciding which classification is appropriate for the site, the decision usually comes down to two factors: complexity and flexibility. SCME is the right choice when the site has multiple resources that require individual metering, when DLC is needed to manage losses centrally, or when the resource owner anticipates changes to the metering configuration in the future. And ISOME is appropriate for simpler sites where KISO's direct polling capabilities are sufficient and where the resource owner does not require the additional flexibility that SCME provides. And just to quickly summarize the ISOME and SCME section, these classification describes who is responsible for meter data quality and how the data reaches CalISO. They do not describe the physical metering hardware. ISOME means KISO takes direct responsibility through pooling. SCME means the scheduling coordinator takes responsibility through a managed submission process governed by SQMD plan. The DLC is only compatible with SCME due to the complexity of its calculations and external signals to the meter. So any convergence between the two classifications requires a careful evaluation of the site, complexity, calculation requirements, data ownerships, and compliance obligations. And finally, just to sum up everything said today, we've covered a lot from how losses are handled to where meters are placed, to the three metering methods and how those tie into ISOME and SCME, and the different ways a resource can participate in CalISO market depending on how that system is designed. So if you look at things where a few years ago, most of the sites were pretty simpler. Single resource setup, straightforward metering, fewer decisions to make. Now with multiple resource sites, PV paired with storage, and more complex interconnections, the meter side has become a lot more involved and a lot more important to get right very early on. So the main takeaway, if your site has level of complexity, evaluate your metering approach seriously and early. The 24 and the 18-month planning window aren't arbitrary. Getting this wrong late is expensive, and sometimes it requires renegotiation contract that are already signed. And this is where the decision goes beyond engineering. The metering method you choose affect your settlement accuracy, your KISO compliance posture, your PPA terms, and your operational overhead for the life of the project. Getting it right from the start protects you from commercial positions. And with that, I'll open up for questions. Happy to dig into anything we covered today. And if anything we covered today is directly related to a project you're working on, whether that's method selection, classification convergence, or just making sure you're on the right track on the right timeline, we here at GridU would love to schedule some time to go through it in more detail. Even a 30-minute call early on can save a lot of headaches down the line. So don't hesitate to reach out and we'll get something on the calendar. So if anyone has any questions, I'd be more than happy to answer them.
It looks like we can kick it off with a question in the chat. We have one dropped in there earlier.
ISO applies oxaload combinations. I believe they're asking how does KISO applies oxaload compensations for the best systems with integrated aux loads available to read as data point from the best controllers. So if you're having a peer-to-peer resource continuing with the best and the best aux, majority of the time you would initially have a best aux meter there, or an external signal whenever your best is idle would be sent to the best meter, so the best meter can stop recording the retail energy, and it'll be all billed to your best aux meter. Excuse me. Like I was saying, when the best controller sends a external best idle signal to your best meters would initially stop recording any energy being delivered to that meter, and your best aux meter would start recording energy that is being used for your best aux meter.
If I could jump in here too, I do see that this question is about compensation for the BESS and BESS aux for an integrated. If it is such that the BESS aux load is behind the BESS meter, such that BESS and BESS aux are aggregated at the meter, compensation will apply to the meter, to the POI, no matter if it's accounting for BESS aux or the netted value of the two.
Thank you.
The next question, does grid forming best need special metering with specific waveforms capturing capabilities? Tenor.
Yeah, so I think I could take that one too. So the metering that we're talking about in today's presentation is specific for CalISO revenue metering. There are some Appendix H requirements that do require waveform capture, but that is not the kind of metering that we're discussing today. If we want to separate out Appendix H requirements into a different conversation, that would be where that would be more suitable.
Do we have any other questions for Inder here? Okay, perfect. Well, thank you everybody for joining us today. Like I said before, the recording will be available on our YouTube channel in the next few days. And if any additional questions do come up after the webinar, please do not hesitate to reach out to us. Thanks again, everybody, for joining, and we hope you all have a great rest of your day.
Thank you, everyone.
Thank you.